Welcome back. If you remember, we are trying to extend layer 2 over a layer 3 network running between two close by cities, Miami and Fort Lauderdale. And we are trying to do this to move VMs across them. We will be using ACI multipod to accomplish this, having Miami as pod 1 and Fort Lauderdale as pod 2, and then letting ACI automatically deploy VXLAN between them. In part 1, we went through the main multipod concepts, and I showed you how to configure the interpod network, or IPN. We will now finish our configuration by running the ACI multipod wizard. But first, let's review our topology. As you may remember, I currently have a working ACI setup with 2 spines and 2 leaf nodes connected to a single IPN device in the Miami pod, which will serve as pod 1. In addition, I have already cabled and powered on 2 spines and a single leaf on the Fort Lauderdale side, which we will discover and configure as pod 2. At this point, neither the spines nor the leaf on pod 2 have any configuration. They are just powered on and waiting for an APIC controller to configure them. In order to successfully finalize my multipod setup between these 2 locations, I will run the multipod wizard twice. The first time, it will configure the connection between the spines in pod 1 and the IPN node. And the second time, it will specify the configuration to be pushed to the spines in pod 2 connecting to the respective IPN port. Let's start with the pod 1 spine nodes then. Go to Fabric, Inventory, and in the Quick Start section, click Add Pod. This is what I have been referring to as the multipod wizard. As it pops up, there's a warning saying that pod 1 connectivity to the IPN is not yet configured, which is exactly the reason why we are using the wizard, since the IPN node, in my case a Nexus 9000 standalone switch, is already configured as we covered in part 1. Let's click on Get Started now. We first need to specify the spine ports that will be connected to the IPN. In my case, we have a couple of spine nodes, spine 101 and 102, and they are both physically connected to my single IPN node called N9K IPN Site 1. Let's start with spine 101, which is using interface E161 to connect to my IPN node. We will assign IP 172.16.113.1/24 to it, since .2 is being used by the corresponding IPN switch port, which in this case is E153.4. I will set the MTU to 9000 and will now add the other spine node, which is spine 102, using its interface 161 to connect to the same IPN node, but on port E151.4 this time. Great, IP addresses are now configured on my spine interfaces. Let's click Next and enable OSPF on them, which is the underlay protocol we configured on the IPN switch. We have to make our spine and IPN settings match. Therefore, I will set OSPF area 0, and we'll also have to define point-to-point as the network type. We can adjust the OSPF network type by creating an OSPF interface policy. I could also adjust other values, like MTU ignore if I wanted to. Let's now click Next, and now, to finalize configuring our pod 1 spines on the Miami site, we need to specify the external tab pool. The external tab pool will be used to dynamically assign a router ID to each spine node, and a common address representing all the spines in the pod, which is also known as the Anycast tab address. The router ID is used to establish MPBGP EVPN peerings with other pods, while the Anycast tab address will be used to serve as next hop for all the EVPN prefixes it advertises to other pods. Keep in mind that the subnet mask you want to configure for your external tab pool must have a length of between /22 and /29. In my case, I will use 172.16.100/24, and the corresponding values should be automatically populated. Let's click Next, And as you can see, a summary of the configuration that will be automatically created by the wizard is displayed. This includes the access policies or physical network configuration for the spine nodes, such as the VLAN pool, AEP, switch and interface profiles, and policy groups. We can also see that the L3 configuration for my spine nodes will also be automatically applied. If we had not used the wizard, we would have had to configure all this manually, so it definitely saved us some time here. You can always change the name of these items if you'd like. I will now click on Finish, and we are done configuring Pod 1 spine nodes. Let's verify that our configuration is working then by going to the IPN switch. By now, we should have established OSPF peering with both spines 101 and 102. And as you can see, OSPF peering is successfully established. We are done with Pod 1. Let's now proceed to add Pod 2, which represents Fort Lauderdale. We will run the same multi-pod wizard again. I can either click on Add Physical Pod right here, or close the wizard and open it again from the Quick Start menu, as you already know. Either way, the wizard will identify that Pod 1 spines are already configured and will allow us to configure additional pods. The top part does not say the spine nodes on Pod 1 are not configured anymore. Instead, it gives us a recommendation to keep our QoS settings consistent along the way. And if we now click on Get Started, we can see that the wizard is now asking us for the pod ID we want to assign to our new pod. In this case, we will go with Pod 2. We also need to specify a tab pool for this pod, so that APIC can assign an internal IP address to each one of the spine and leaf nodes discovered on such pod. This step pool should be different to the one you assigned to Pod 1. Now, add the spine IDs you will use for your spines on Pod 2. At this point, we have not registered spines 103 and 104 in the fabric, and because of that, you will not have them showing in the drop-down list. But don't worry, this is totally normal. You can still pre-provision them by typing the node ID you plan to assign to them once they are discovered. Just like I did with the spines on Pod 1, I will have to specify the interface each Pod 2 spine will be using. In this case, both spines are connecting to the IPN device on port 131. I will also specify an IP address for each of them. And then, just like I did with the spines on Pod 1, I will enable OSPF with its corresponding network type. Finally, I will also specify an external TEP pool for Pod 2, which should auto-populate the router IDs and Anycast TEP values, and then I will just click Next and Finish. It seems we're ready. The spines on Pod 2 should already be requesting an IP address to the APIC via DHCP using the DHCP relay configuration on the IPN. Let's verify that by going to Fabric, Inventory, and Fabric Membership. In the Nodes Pending Registration section, 2 spines are requesting to join the fabric, which are the 2 spine switches on Pod 2. Let's register each of them. I will add a name to my first spine, I will assign it to Pod 2, and I will make sure that the node ID I specify is the same I put on the wizard. In this case, we have 103 for the first spine, and then 104 for the second spine. After a few seconds, they should show as active. If I now verify the OSPF neighbors established on the IPN node, we will see the spines on Pod 2 showing up as well. But what about BGP EVPN VXLAN, you may be wondering? Let's go back to APIC and click on the infra tenant. We can see that an IPN L3 out has been automatically created in the Overlay 1 default BRF. And if we click on one of the L3 out configurations for one of the spine nodes, in this case spine 101, we can see we have established BGP sessions with other nodes already. Let's verify this by logging into spine 103 in pod 2 and perform a show IP interface brief for all VRFs. We can see that loopback 8 is currently assigned with IP address 172.16.200.3. If we do the same for spine 104, we see the .4 IP address assigned respectively. Confirming spine 101 on pod 1 has BGP EVPN peerings with both spines on pod 2. Now, if we take a look at the IP address on interface loopback 7 for both pod 2 spines, you may see that they have the same value, which most likely means that .2 is the Anycast TEP address representing the pod. Going back to APIC, you may notice we do have other BGP neighbors there, such as 10.1.112.64 and 67. Why? Well, as you may remember, BGP is also used in ACI to redistribute external routes learned from border nodes to the rest of the fabric, as we covered in Module 3, Episode 3. Therefore, those two addresses correspond to the two leaf nodes in our fabric, as we can now see on their corresponding CLI output. Let's now go back to Fabric, Inventory, and Fabric Membership. We should see that my leaf node on pod 2 has also been discovered. I will register it as leaf 203, and after a few seconds, my pod 2 should now be fully operational and all nodes should be active. If I go to my topology, I can now see both pods with their corresponding nodes, allowing me to manage both Miami and Fort Lauderdale as a single logical network and extending VXLAN across them. We are now ready to try our vMotion between both cities or pods using our automatically created VXLAN tunnels. In the interest of time, I have already provisioned a VMware server on pod 2, connecting it to leaf 203 on port 115. As you can see, all the physical network configuration or access policies for this switch and port are already there, including switch profile, interface profile, and policy group. And I am reusing the AEP and VLAN pool I had previously defined for my pod 1 VMware VMM connections. If we now move to the logical network configuration, I was already using a tenant called Extended Network on pod 1, with an EPG called Extended Web, which is associated to my VMware VMM domain. This EPG is currently associated to two VMs, MIA Lav Prod 1 and MIA Lav Dev 1, which are running on the 1096.473 ESX server on pod 1. In addition to .73, I also have .74 running on pod 1. And then we also have .83, which is the new server I connected to leaf 203 on pod 2. And as you can see, it currently has no VMs since I just provisioned it. Let's open a console session to both VMs currently running on pod 1 and verify their IP address and current connectivity. As you can see, they both have connectivity to their gateways, which was configured as a bridge domain subnet, and between them. On the prod VM, I will keep the ping to the dev VM running, and I will move the dev machine from Miami to Fort Lauderdale, which means I will select the .83 server as my destination. We will leave all settings as they currently are, since we are assuming the network is extended all the way to Fort Lauderdale, leveraging our ACI multi-pod configuration. Once vMotion successfully finishes, let's go back to our prod VM console. As you can see, I did not lose a single ping in the process. And if I go back to my APIC, I can also see that my VM is now learned on node 203 interface 115, which belongs to pod 2 in Fort Lauderdale. We successfully extended layer 2 for the 1110 network across two different locations separated by an intermediate layer 3 network without investing in dark fiber installations, LAN-to-LAN services, or other similar data center interconnect technologies. And the best part? is that we kept both data centers under the same management console as a single logical network. As a summary, multipod can be useful when you need to extend layer 2 across multiple locations or rooms for data center migrations and active-active data centers plus many others. Whether you choose to connect two pods back to back or have multiple pods connected through an IPN, make sure you check that your multipod environment meets the round-trip time and multicast requirements, and this should be quite straightforward.